Hello, my name is Haidar Osamo, and today I'm gonna show you how to simulate ultra high performance concrete beam by ANSYS. Here we can see first of all the studied beam under 4-point bending test. The width of the beam is 100 millimeter. The height of the beam is 200 millimeters, and the length of the beam is 1500 millimeters with a simply supported span by 1400 millimeters. The tension reinforcement there were two bars, main bars here with 25 millimeters, and inclined shear reinforcement was 16 millimeters. Maybe you ask why we use this reinforcement just on one side. In our experimental test, there were two DIC cameras, digital image correlation technique, and we concentrate with these two cameras only on one side. So to ensure that the crack will start from this side, we use this reinforcement here to delay and stop the propagation of the cracks. Okay, then we will start to show how the process will be in ANSYS. Then I have downloaded now the last version at 2019. So we will follow these steps, this process, okay, one by one. First of all, we start with preferences, and we click structural, okay, reprocessor, and we need to define then the element type and material properties of the studied beam. Element type, add, then we choose for concrete is 65, select 65, and for the steel plates, this is the steel plates, and the supports also from steel, okay. We'll choose element number 186. In the previous version it was solid 45, but you can't use it in this version. And to define the element type for reinforcement, we need to define the link section, because it doesn't go with this list in this version. So we go to section, link, add 25 for 25 millimeter. We can call it 3 bars, and the area is for 1 bar is 9.7%. Okay, and we do the same for stirrups, 60 millimeter. Okay, stirrups, link area is calculated. Well, of course you can use the same program to calculate it. If you divide 3 by 4 like this, it will calculate it. Okay, then we go to real constant. We just allowed to do real constant for slide 65. we can call it 150, referring to the compressive strengths of ultra high performance concrete, the usual one. And here we have rebar 1, 2, 3, which refer to 3 layers can be established through solid 65. This can represent the fiber volume as a percentage of cross section, in addition to the orientation of this fiber. So we can simulate fiber by entering the volume ratio and by entering the angle, and by putting this in 3, or by putting this in 3 layers. So, or this can be also used to simulate the rebars, as it can be also in 3 layers, and we just enter the percentage of this reinforcement. But in our case, I would choose to be pure concrete. Then we will not have any values here, it will still 0. One thing more I should talk about, it's crushed stiffness factor. This, if you enter this, for example, 0.1, then you tell the program that you want the concrete to still resist by 10% of its original strength after failure. So after failure, it will still work by only 10% of its original strength. Okay. In this case, we keep all 0. And now we move to the third one, material properties. We should define the material models to reflect the non-linear behavior as possible. So first of all, we make a new model. We call it, for example, 600. This will be for main rebars and for stirrups steel. Okay, we can delete this one. Always one should start with linear elastic isotropic, even if you will define non-linear, so you should start first with linear solution. We can take it to 5 and Poisson ratio for 0.3. Now we go to non-linear, inelastic, rate independent, isotropic hardening, ANSYS plasticity. We go to bilinear in this case, and the yield stress we have from the lab was 600 megapascal. And tangent model, this refers to the hardening of the steel, if there is hardening or no. It doesn't affect the result so much, or almost doesn't affect the result in this case. But if you enter it 0 and you can plot the graph, you see it's totally horizontal. If you enter it 500,000, for example, then you saw how it's coming up, referring to the hardening of the steel. So we can keep it 1000, for example. It doesn't affect so much. Okay, and now this will be for rebars and stirrups. As we add a new material, this will be for plates. We can call it 200, for example. For plates, we use only linear. There is a Poisson ratio of 0.3. And now we will define the most important part, which is the concrete. For the concrete, we need to define linear first, and then we go to the non-linear behavior. For linear behavior, isotropic, Young models here, if you are going to use non-linear multi-isotropic model, which include stress-strain curve, then you need to define your model based on stress-strain curve. I will use it in this case, so I can't, this young model here, or model of elasticity, well, it's not from the lab, it will be defined by me, so I should choose this value to be in good to reflect the stress strain curve, as I can show you here. Let's say we have this one. This is stress, and here is strain, and we have this one. Let me see this first. Okay, so here is stress, sigma, here's strain, epsilon, this is the curve, and this is a tangent. This angle should be equal to Young model. To do this, so we take to draw this stress strain curve, we have point stress strain. Okay, we should divide the first 2 points, stress and strain, to meet Hooke's law, and then we find E, which will be used in ANSYS. So as I calculated, to do this, to draw stress strain curve, I need to use this equation, which was used by Rabiel. This equation reflects the non-linear behavior very well. This is to draw a stress strain curve. This E can be obtained from lab test or by using a formula from literature. I would recommend you also to use Rabiel formula for Young model. It was 3,840 divided by compressive strength, I think. So this is the values that was obtained from the mentioned formula, and by dividing the 2 first points, as I said before, we should get the first Young model for linear case. Otherwise the program will not solve. I can find this formula for Young model and show you. So here is the formula that I mentioned. it reflects also the young model of ultra high performance concrete material with very high accuracy, I think. Okay, so if we come back to the 1% fiber, then we can use this value. Okay, so we take this one now. Several researchers mentioned that Poisson ratio for ultra high performance concrete could be around 0.2, so this is what we will use. Okay, and now we go to multilinear to define stress strain curve. So the same as steel but not bilinear, multilinear. We have 6 points, and by the way, we can find stress strain curve either by this formula that I mentioned, or from load displacement curve. By dividing load by area we get stress, and dividing displacement by length we get strain. Okay, but so this is the values now. We enter it, you can just do copy paste, and also if you have more than 102, like 1 or becomes negative, like 188, like this, so the negative portion should be taken away. Okay, so this is now we come to the most important model also for concrete, for non-metal plasticity concrete, where this model depends on William Rankine theory. We have 4 main parameters for crack and for stresses. Usually the value for open and closed shear transfer coefficient is between 0 to 1. When it's 0, this means it's very smooth. When it's 1, so we have high friction. From the literature also we can find that for open shear they usually take 0.2, and for closed shear they take 0.8, but it's allowed to change them to fit your case. So you can decrease this one, increase this one, to find the best solution for your case. For cracking stress, it refers to the tensile strength, which can be obtained by several formula and in the lab by a 3-point bending test on small prism. In our case, it's 18 megapascal, and crushing referring to compressive strength of the material, which is 105 megapascal in this case, and tensile crack factor is recommended to be used 0.6 by the help file of ANSYS. Okay, and then there is another way to do this by taking crushing stress -1. If you do like this, then will be just cracking failure, not crushing failure. And several researcher mean that if you take it -1, it's more reality, because when you give the crushing which is the same as compressive strength, if you give it a value, then they meant Poisson ratio will make a big effect. What does this mean? If we have this element in ANSYS, okay, and this is the load from the 4-point bending test, this element when it facing compressive, then it will be like this. Okay, this will compress the neighbor's element. So this will crash, compress the neighbor element, crash due to Poisson ratio, which make the failure before its reality, before with a lower strength than the experimental one. Okay, so several researchers prefer it to be -1, but since we take it from the lab and we did the test, so I'll keep it the real case 105 megapascal. So here we defined our models, and now we need to draw the beam. So this is for concrete, plates and supports, and this for rebars and stirrups. Now let's move on to draw. So everything can be established through modeling, and everything has to be volume. We go to modeling, create volume, plug, and by dimension. You have free to try this also, what you will be and what you will reach. I'll use by dimensions. So since we have width now of 100, I can show you again. Width 100 millimeter, 200 millimeter height, and 1,500 millimeters length. Okay, so for X case, I would choose to be the coordinate. I would choose it to be in the middle here, in the middle of the beam. I'll draw the beam at this base, so it will be in the middle, and then I will give the program the order to draw it. So I'll show you how. So for X, it will be -50 with +50. And this is the width. For Y, which is the height, it will be 200, isn't -1 and +100. For length, so Z is the horizontal axis. Okay, Z is the horizontal one. And I have 1,500, so -750 and +750. Okay, and we click apply, and then we click this 3D. So we have now the beam. It's very easy. If we go again to dimension, and now I need to draw the supports. If we suppose that this is 80 millimeter with a 30 millimeter high, so 80 30, okay, for all 80 30. Then by similar calculation I can show you also. Width is the same. The height, since we will start from the support which is down, so minus 30 and with 30 minus 100 with 30 thickness, so it becomes 130. Okay, and for the length becomes, we can calculate it like 705. Okay, this is the length of one part of the beam, minus 80 plus 40, half of the length of the support, or the total length of the support. And 750 minus 80 minus 40. Now we should get the first one. Apply. Where is it? And for the other case, the other support will be the same width, same height, but we will take it in minus since it's in the negative part of the axis. So take minus okay, so here is the two supports, and now we need to draw the two plates which will transfer the load to the concrete part of the beam. So also it's the same width, but the height now in positive, since we are over y and the positive part of y. So 100, 130, and for dead, since we have it here, it's was it 600 between the supports, 600. Okay, so we will take it 600, main 300 in the middle, 300 plus 40 and 300 minus 40. Why? Where is it? It's the same case with minus for the other one. Okay, here we are. So here you can see it in different views. So now we draw our beam. That wasn't so difficult. Now we need to divide the beam in the same places of rebars and stirrups. Okay, how to do this? So we go to create create so now we need to divide the beam, so we go to operate booleans, divide volume by area. Since we have volume, we need to divide it by area. Okay, now we can just choose the face to this deselect this one, click the right button of the mouse and so we should just click it to, this is the best way to choose it, and you find that everything is chosen. So that's wrong also. So I've tried several times to divide by volume, area by volume by this way. It doesn't go Well, anyhow, there is several other way, but by this division you just click by this one, this face, okay, and then you enter the cover. We have the cover of 20 millimeter, then you enter minus 20. This is all what you need. There is another way to divide, to determine the rebar position and divide everything you want in the beam, and maybe it will be more accurate method, which is work plan method. Okay, so if we go to work plan, to volume by work plan, so divide volume by work plan. If we go to volume to work plan, and then offset work plan to key point. And then let's choose so work plan to offset work plan to key point. You can choose this part. Okay, do you see? So we have Y, Z, X. Okay, so one thing one should be care about. Work plan divides the beam only in XY plane. Therefore, if I want to divide horizontally, then XY must be horizontal. Okay. So now we go again to work plan, divide or offset work plan by increment here. Then we need to change it to 90, because if we now make a rotate, it will be by 90 degrees, not only in 30 degrees. Okay, so we make rotate around X axis, and as we want to divide horizontally, so here we have XY horizontal. Okay, now I should move it down 20 millimeter to make the cover. So this will be down 20 millimeters to make the cover of the beam. So in this part we can write 0, so minus 20, because it's against y-axis. Okay, see until it becomes down 20 millimeters. Now we can go to modeling, the same thing, divide volume by work plan, equal, here we are, so it's been divided. So this method I like it the most, more accurate. Now by the same way, to make the cover for the under part, so we use work plan, so we make offset work plan, or offset work plan by increment, so we did 0, 0, minus 160. Because we have 200 height, 20 millimeter cover up here, and 20 down, so 40. 200 minus 40, 160. Okay, and volume by work plan equal, so we have no cover. The same can be made for the vertical case. So if I need to divide vertically to determine the cover of the beam, so XY should be vertical. If I want to divide horizontally, XY should be horizontal. Okay. So I can do it by this. Give the last order. If I go to work line by increments. Ice hiding. Okay. So now we give it 90 degrees, and we should rotate the coordinates or axis so that XY become vertical. To do that, we just rotate it around Y axis like this. Oh, now we have X, Y. I would prefer to have Y in this. So maybe if I do like this. Oh, it's Y now, so this is XY vertical, it's okay. So, for example, if I need a cover to be 20 millimeter in this way, then I need to move the local axis to 0 x 0 y and minus 20 because we work now on the local, not on the global, so that wasn't the right way. So work plan increment, so we can get it to 0 0, and now on y now, so on x 0 and y plus 20 and z 0. From here we can get volume by work plan equal, so it takes like xy, you see it, so as you can see here, so 20 millimeters cover, 20 millimeters cover, 20 millimeter cover. We need also 20 millimeter at this side, so by increment 0 0 and minus 60. We still work on the local, and now okay, volume by work plan equal, we have another 20. Okay, if we take it like this one, here is a concrete part from here, here is the plate support, okay, and 20 millimeter covers here, 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 and this one. Also, we can use the same way, since I don't have any important stirrups in my case, so I don't want to divide it by the position of the stirrup, since I don't have it. But if you have stirrups in your case, so you just move this local axis to the points where there is a stirrup. Okay, for example here, and divide we call, here divide we call. Or you can use divide, or there's another way to use it, but as I said, I prefer this way.